You can see I selected quite a controversial title, but this is because I hope that after this presentation, we can start a discussion on other case studies and experiences in the topic of machine learning applied to naval architecture or marine engineering, so the maritime sector. And as you will see in the presentation, there are some goods, some bads, and the aim is to start a bit of a discussion on this. So, okay, wait a second. Yeah, perfect. So I will start by looking into why talk about machine learning, and in particular on the background for the maritime sector. And then we'll look at a couple of case studies that both use machine learning, so there are applications of machine learning, and to deal with underwater gliders. So we'll introduce what these vehicles are, if you're not familiar with them. And finally, I'll conclude with some lessons learned from these case studies that hopefully will help you with your applications to avoid mistakes or to learn from good things that work well. So first of all, the reason why I'm looking at this is because there has been a growing interest in artificial intelligence, and machine learning is a subset of artificial intelligence. So we can see from Google Trends that there has been a steady rise over the past decade of basically looking into artificial intelligence words, such as artificial intelligence, data science, machine learning. But this is also reflected in more practical terms into the growth in patent applications, for instance, in Europe. We can see that for computer technology, they increased by 4%, but this is mostly due to a growth of 29% over the past, 4 years, for which the data is available in machine learning. And this is also reflected in a growth in research articles. So this is from an academic perspective, but it's also reflected in actual monetary investments by companies, and the data for 2019 is incomplete. This is taken from The Economist, but we can see a steady growth in funding for AI applications. And if we're looking at sectors, they're very diverse. Mostly it's autonomous driving, but there's also like security, there's there's the healthcare sector, there's finance sector, and so on. And what we look at today mostly is the maritime sector. So we started to see that everything looks to be hunky-dory, everything looks to be perfect with machine learning, but in reality, is that really the case? Are there no cons to machine learning? And this is probably what the artificial intelligence company want to sell to you as an idea of artificial intelligence. Everything is super clean, everything is really nice and working well. In reality, for experts, we can see that this is actually more the case. So the problem is, there's a problem of transparency. Sometimes you don't understand why a machine learning system is giving you the result it's giving you, so it's very difficult to interpret the result. But also, there are people that just apply it as a black box, and so it's very difficult to use it. And additionally, there are problems with robustness and proofs of stability. So basically, there are a lot of things that are not, basically, they need to be taken with caution, and we need to be cautious of. And one of the biggest problems recently is actually the steady, like the exponential growth in cost. And so we're going to look at computational cost, but also in terms of revenue. So here, what we have is the timescale from 1960 to 2020. And here we got a logarithmic scale, and this is a computational cost. And what we can see is that artificial intelligence application in terms of computing power needed a requirement that was doubling every 2 years. So this is in line with Moore's law. But recently, as the capability has increased dramatically, so actually have the cost. And so actually what's happening here is we've gone from Moore's law into a stronger exponential growth. And this means that we need to use more powerful system with a much higher cost. And to make matters worse, even when we're talking about actual revenues, this is a study done in 2019 by the Sloan Business School of MIT that did a survey of big companies making investments in AI, basically whether it actually gave them a return on investment or not. And they separated between IT companies and very innovative startup companies and more traditional finance or healthcare companies. And what they could see is that only 50% of the case for high-risk projects, so for IT companies, it actually provided a return on investment and increase in revenue. and only 23% of the case was for low-risk projects. And to be honest, I would imagine that with ships, we want to be relatively conservative because we're designing very, very expensive pieces of kit that are actually pretty new and prototypes. So it's true that it could be a high risk, but we want to decrease the risk as much as possible. So machine learning sort of like should raise an alarm bell in this case if we can't really see a big return on investment there. So now we're starting to look into machine learning and coming to the maritime sector. And actually, what is machine learning? So it is a subset of artificial intelligence, but it's basically defined as the study of computer algorithms that improve automatically through experience. So the idea is we're no longer prescribing what to do for, say, the controller on the ship or a design algorithm. We're actually getting the algorithm to learn by itself what it should do to get the desired behavior. And here we got a list of, I tried to categorize it into the main applications. And I tried to use examples I'm familiar with from the Marine Research Group at UCL, but I'm sure that your companies or your group have probably looked into different applications, and I'm happy to hear about them after this presentation. So the first category is supervised learning, and I think this is quite important to understand before we move on to the case studies. So here, it's a task-driven problem. So what happens here is that you have a set of ground truth and you provide them to the algorithm, and the algorithm has to sort of learn and determine for new data points what basically what their value should be. And we can split into two main groups as well. So we have classification and regression. Now, classification means that the algorithm needs to determine to which category or class a point belongs to. So for instance, I don't know, I've got on my phone an app that if I take a picture of a leaf of a tree, it will tell me to which tree it comes from, like what species. So in that case, what it's doing is it's doing some image pattern recognition, and it's associating it with a prescribed discrete category. And the examples that we looked at that work quite well for us are, for instance, fault diagnostics. So looking at classifying faults from an FMEA for a particular marine autonomous system, that's the application, but it could be anything else. We're also looking at ship design recommender systems. So one of my colleagues started looking into, for instance, determining, given a set of ship characteristics, whether you should have a bulbous bow or not. You can also look into, some other of my colleagues looking into ship movement classifier. So basically recognizing from the satellite data what maneuver the ship is doing. And this could be used to determine rogue behavior inside like the extra economic zone. But it could actually be used for any time series classifier. The different solution is still within supervised learning is to look into regression. So regression here, we're trying to determine a continuous value. So we're trying to estimate a continuous value. And for instance, we could be, I don't know, predicting the price of a house given its size, given its location, given the number of rooms, etc. Now, applications for the maritime sector that we looked at are, for instance, for propulsion power prediction, predicting biofiling levels. And we've done this for both small-scale autonomous underwater vehicles, but also large-scale ships. And with a large operator, we've been able to look into when to dry dock, when is it actually optimal for that class of ships to dry dock for those routes. But you could also, we also looked at something different, which was incoming wave force forecast. This is mostly for offshore renewables. I have to say that for ships traveling at a particular speed, this is actually more challenging. And for prognostics, so predicting when maintenance is required. Then a completely different set of algorithms falls under the unsupervised learning category, and this is data-driven solutions. So these sort of try to push the boundaries of what is possible with AI, but obviously it's more difficult to train them. Their accuracy is also a bit less than supervised learning approaches. So here we've got two main branches. We got dimensionality reduction and we got clustering. And in dimensionality reduction, we're looking at anomaly detection. So for instance, what are the main fundamental features that we need from our data? And so for anomaly detection, this is great because we can recognize healthy behavior from unhealthy or like damaged behavior. And finally, clustering is very similar to classification. So we want to find the subset of the data, but in this case, we don't know how many classes we have. We don't know what the classes should be. So it's a bit more difficult for the algorithm to understand what are the main features of the data. And so it still can be used for diagnostics or just general time series data clustering. The final set is reinforcement learning. And reinforcement learning is a decision-making process, learning by mistakes. And so here we typically apply it to control applications, for instance, control of underwater vehicles, control of renewables, but it could also be energy management on ships. It's also path planning and navigation. Now, the case studies we're going to look at today are mostly the anomaly detection, and we look at a more general regression problem as well. Now, the two case studies are both to do with gliders. The first is a recommended system for the setup of gliders, and we'll see why we need it, and also an anomaly detection system. Now, underwater gliders, if you're not familiar with them, they're small and simple autonomous underwater vehicles. And they look like this, and basically this is the concept of operations. So the vehicle operates, basically the main propulsion is just a change in buoyancy, which is done through a buoyancy engine. So basically it's typically an oil bladder that extends from the vehicle and that is positively buoyant. And when this is retracted on the surface, the vehicle becomes negatively buoyant and it just falls down. And at the bottom of the dive, it will extend it again. So it will become positively buoyant and it will come back up. And the wings convert the vertical motion into a horizontal motion as well. And this is super efficient. And this is why these vehicles can be at sea for longer than 12 months with a single charge. So this is like pretty impressive. To control heading, they typically either have a rudder, like in this case, but they could also have a rolling mast inside the vehicle. And to change pitch, to change the speed they travel at, they have a battery mast they can control inside the vehicle. And we'll see why these points are important. And then we define each of these things as a yaw, and a dive is between surfacing. And only when the vehicle is on the surface, it will be able to send data to shore, take a GPS fix, and get commands for a new mission. Now, the first case study is a recommended system of gliders. So why do we need it? Like, what is actually the challenge? Now, first of all, let's have a look here at the system developed by the Oceanography Center for the remote control of their vehicles, of their fleet. So here we got the underwater glider that whenever it's surfacing, it basically takes commands by satellite and it sends back decimated data by satellite. It comes to the command and control infrastructure, which is basically a cloud-based center, almost like what you would imagine from remote control centers for ships. And individual pilots or operators can interface with it through their individual computers. Now, the first challenge we're looking at is the setup of gliders. What's happening is the gliders are ballasted and trimmed in a tank, but then when they're deployed at sea, the water properties will change from the tank. And there might be small additions like small appendages in terms of sensors or something that has changed. So what happens is for the first few dives, you need to get data from the vehicle to actually understand how to trim and ballast the vehicle correctly. And to center the controller, so you need to find the center of the buoyancy engine, you need to find the center of the pitch control, of the roll control, etc. And this is actually, sounds easy, but in reality, it's pretty tricky for pilots to get right because you need to have a full understanding of the dynamics of the system. So the problem is that this is really difficult for pilots, especially novice pilots, to learn and do. And the second problem is when operations need to run the clock, pilots need to wake up at night and actually check if the parameters are correct. Because if this is not the case, the data the glider collects is pretty much useless for the oceanographers. And sometimes you can actually get mission aborts as well because the glider experiences some instabilities. So the challenge was, how do we automate this selection of the control parameters and the hydrodynamic parameters for the gliders? And so what I did was I started with a good machine learning solution. So like in a ship design, you start with system requirements definition. In this case was problem definition. I need to find the centers of the actuators. I need to find the hydrodynamic coefficients and hydrostatic ones as well. Then I started with data collection and cleaning. So I got data that needed to be representative. So I selected data from the UK and I selected data from Australia. And I subdivided the data into individual dives. And I cleaned the data by keeping only steady state data because the glider is actually in steady state flight for most of the time. So actually this reduces the number of parameters and the complexity. And then I split the data into training, validation, and test set. So the training set is where you train your system on. Validation set is an unseen set that you use to tweak your parameters to optimize your performance. And test set is the final set, which is not seen until the end, and you want to use it to compare different methods together or your performance against the pilots. And then I applied and selected an algorithm. So in this case, I went for deep learning because I had more than 8 million points. So I know that deep learning works good for more than 5 million points, which is a lot, and this is something we'll cover. But it was suitable. I was able to simplify the method to a fit-for neural network. You can ask me about it later. But basically, this is, I'm using the steady state data. So what I was able to do was able to remove the time dependence and simplify the problem to constant data samples. And then I selected input from the dynamics and the control input of the vehicle and output the parameters I wanted to find. And then from this, I implemented it, tested it on the data I had, I deployed it. And obviously at this stage, you would imagine that everything went well and it went into success. And so this is it. Well, I wouldn't have a controversial title for my presentation if this was the case. What unfortunately happened was that I wasted 4 months of my work on this because I got a behavior that was really unexpected. So the algorithm seemed to be working really well for some cases, but sometimes it would make predictions which were really strange. And I found that the hydrodynamic coefficients never varied. So there was something definitely fishy going on. And it turns out that actually by delving deeper into this problem, some of the pilots of whom I used the data actually were not checking the vehicles all the time. And some parameters may not be updated for days and sometimes incorrectly. So I'm not going to say which pilots were involved, but basically this sort of told me I don't fully understand this problem. I should have actually understood it better to try and develop an improvement on this. I just use machine learning by the book. So this is like what you probably would expect from an IR company trying to develop a solution off the shelf for you. And in this case, unfortunately, it didn't work. So what I did was I went back to the drawing board. I delved deeper into the literature. I fully understood what the manufacturer's manual, the recommended practices for pilots were. I understood what the controller behavior was. I understood what dynamic models other people developed for specifically for these gliders. And then what actually became obvious was that in this case, yes, machine learning could actually work because I had a lot of data for it. But in reality, here we were not looking for a complete revolution. We were just looking for a few improvements on the status quo because a dynamic model was more sample efficient and it was more likely to give me the behavior I wanted just because the vehicle was fully understood and with prescribed motions. So that's why I decided to go back to the drawing board, start with a model-based solution, split the control centers and hydrodynamic parameters, and clean the data. So obviously the descents and ascents to look at the pitch and roll control, the bottom of the dive to look at the buoyancy control to try and find the center. And then I selected a simple linear regression because the controller was actually only a P controller. So that it was that basic. You just needed to make a linear fit to try and find the center for that controller. And then obviously tested it with the 12 deployments I had and compared it against the pilot's responses. For the hydrodynamic parameters, I cleaned the data, kept only the steady state flight data, looked into the dynamic model of the gliders with a few changes to actually account for changes in buoyancy, and looked into a nonlinear iterative solver and benchmarked as well. And the results were really impressive. So actually what happened was that what we can see here in these plots, the blue line is, for instance, the center of the buoyancy engine. We can see that we get a very similar response to expert pilots. And the same for the pitch control and the same for the roll control. So actually the behavior is really good now. And the second thing was that the system was now able to detect changes in the hydrodynamics due to, for instance, marine growth. This actually was what stemmed our research into marine growth and biofouling and dry docking. It's because basically the pilots never changed those values, but in reality, The vehicles, when they got big appendages, their hydrodynamics changed completely. When they got a lot of marine creatures growing on them or seaweed, like in the Coral Sea, that makes a big change. And so all of a sudden, we started to get a fuller understanding of the problem and everything worked well. And the system was actually implemented on the command and control infrastructure and solved the problem. So what are the lessons learned from this in success of machine learning? Well, I think the first thing is when you have a new problem to which you want to apply machine learning to, basically don't expect it to all of a sudden make a massive improvement. Like, don't expect it to solve your problem by itself. You need to be asking the right question, and actually you need to be framing the problem the correct way for machine learning to learn what it should. And that's why it's fundamental to actually understand what the problem is before you try to apply machine learning to it, because otherwise, I can tell you from this experience, your results are going to be miserable. Second thing to look at is your data set representative and large enough? So in my case, it was large enough. So basically, I selected the correct method for that data set. I know that with 8 million points, deep learning was supposed to have high performance than machine learning, classical machine learning. But if I was looking at 10,000 points or 50,000 points, classical machine learning would have been better. And if we're looking at less than 10,000 points, statistics or classical methods like dynamic models, they're more sample efficient. They're the way to go. So this actually is raising more alarm bells for ship design, because we know that we have very few ship designs available. And so we're basically developing things from a design perspective from new. And so that's why data set is not that common there. We basically, it still takes a bit of time. You need to generate a lot of cases to be able to use machine learning for them. The second thing we represented in the data set is not to have a biased data set. So what I mean is, let's say we have anomaly detection. Typically systems are very reliable. And so 99% of the data tends to be for a healthy system. If you use a typical machine learning application, supervised learning classifier, with a data set that has got 99% of the points healthy, that algorithm is likely to tell you every single point you put into it will be healthy, even though it's not. So you will need to basically think about this bias in the data set when you develop your applications. And there were some really popular big failures from Google and Facebook on this. Now, the second case study after this success of machine learning is trying to spin a bit of a more positive story on it. And so this is the anomaly detection for underwater gliders. Now you can see that here we got a different type of underwater glider, but that's only because of the data set I had that was a bit more interesting, but it's the same system using the remote control center. And here, the challenge is that pilots need to monitor the vehicles around the clock, and they also need to decide on recovery action after adverse behavior is detected. Now, what we're going to focus on here is only the first stage, which is something we've already deployed and developed, but the second stage on recovery is still future work. Now, the problems is that, for instance, the Oceanography Center is a relatively small operator, but they already have a large fleet. They already have more than 35 to 40 vehicles. And they have many vehicle variants. So this is the very big difference from, say, the aerospace sector or the automotive. We do have not only many types, but also many variants for each type. So it could be sensory packages, it could be appendages. Basically, every system is almost tailored to itself. And on top of this, the systems are actually under-actuated and under-observed. So they do not observe all the signals you would like them to observe because they don't have enough sensors. And then you also have a big range of failure modes and effects. Some of them are even like completely unknown. And so round-the-clock operations are challenging. And so that's why we started to look into a system that autonomously detects anomalies and flags this to the operator. With full diagnostics, hopefully this system will be able to tell exactly what is wrong so the operator can take a decision and fix it. And in the future, the recovery will be autonomous too. Now, the data sets, as I mentioned, we're using the data sets from these different type of gliders, which are known as LOCAM. And the reason for that is because we have healthy baseline behavior, but over the years, because of the many operations, the Oceanography Center were able to collect a number of adverse behavior that was not detected by the expert pilots during the missions. And so these could be wing loss. It was actual biofouling, but also we did some field tests and field trials for simulated biofouling, something like turbulence stimulators on ships. on ship models of visiting tanks. And then large appendages could be sensory packages and strong environmental disturbances. And now here, learning from my previous mistake, I started from understanding a problem fully before moving to data-driven solutions. So you start from rule-based systems, dynamic models, and then data-driven approaches. So the rule-based systems start from designer's observation of the system, and we'll see an example in the next slide. And basically you come up with bespoke heuristics, so if-then statements. For instance, if this happens, then we're looking at this fault. It's very fast to deploy. However, it's really, really time consuming to design. It took me a month to come up with a rule-based system for a glider for one fault. So that is pretty expensive. Model-based systems are basically also require quite a lot of time from the designer. So you want to develop a dynamic model that works for your specific device. So it's tailored for your device. And the parameters need to be specific for your device. And you're tracking the difference between the model and the system response. It's really fast to deploy, it's robust and simple. And the best advantage is you can apply this for suitable new designs. However, it's really time consuming, like rule-based systems, to design as well. So this is an expensive anomaly detection method to design. Now, the data-driven solutions are very different. They're very general. So the method itself could be applied to anything, like it could be applied to automotive, rails, aerospace. It's basically the same algorithms. But here you're tracking the difference between the actual signals and the reconstructed signals. And ideally, this difference is very low for healthy baseline, but then it becomes very high when the vehicle suffers from adverse behavior. It's very slow to train. You need a cluster to do that, but then at deployment, it becomes fast. And it can be easily scaled, so you can actually increase the number of signals coming in as input very easily, and the system is able to deal with this pretty nicely in a nice framework. However, you need a lot of data, and you need to train the data on the baseline. And then you can apply it even to unseen behavior, and we'll be still able to detect it. This is a bit trickier for full diagnostics, but we're not going to cover this here. So what implementation did I do for the fault detection for the, well, actually, the group, because I can see like some of my collaborators are in the talk. But basically, we looked at a number of solutions to look at fault detection for these gliders. So the rule-based method, for instance, an example is wing loss. How do we detect the wing loss? So what happens is you study the dynamics of the system and you realize that the wing is negatively buoyant, so it's heavier than water. And so when it's lost, it causes a shift in the center of gravity. And as a result, there's a noticeable change in roll between ascents and descents, also because the center of lift changes slightly too. So this took quite a long to study, but we fully captured this effect. And so the anomaly score for the rule-based system to detect wing loss is to track the difference between the mean roll in ascents and descents, because we know that the glider will actually change the heel angle in those. Second method is looking at the same dynamic model from before. So we're using a dynamic model of the glider in this vertical plane at steady state flight. We add a buoyancy offset because if we lose things or if we get things on, such as marine growth, that will change. And the anomaly score basically looks at the difference between the estimated and the actual vertical velocity. Now, in terms of the machine learning solutions, we got the autoencoder and BiGAN. These are the two most promising ones we've seen. So the autoencoder, what we can see is it's a system that takes the original signals and it passes them through a neural network that actually, instead of increasing in size, decreases in size. So what's happening here is we taking only the fundamental information. So this is called latent space. It's just keeping the fundamental information. So if we had 20 signals here we're looking at, say, 4 signals. Those are the 4 fundamental signals. And then we reconstruct it in the decoder. Unfortunately, I can't move that because of the zoom thing, but that's the reason why. And what we can keep track of is the difference between the original signals and the reconstructed signals. This is going to be very low for the healthy baseline because we train on that. But then as soon as we experience some adverse behavior that changes from that, this will increase. A very similar solution is this known as BiGAN. So this stands for Bi-Generative Adversarial Network. And it's very similar. You can see like this is an encoder like here, and the generator looks like a decoder. But the main difference is that here, this data being generated is fictitious. And basically there's a continuous fight between the generator and the discriminator. So the discriminator has to detect if the data being generated is true or false, basically whether it's fictitious or real. And the generator learns how to beat the discriminator. And doing this way, it will learn to basically invert the encoder, and it will learn actually to capture the probability distribution of the data. So it actually captures the distribution of the data, which is something extra over the normal autoencoder, and it actually provides improved performance. So what we can see here are the results. So here we have 6 plots. And these 6 plots are for 6 slocum gliders with different faults. And they're basically listed here. So we got an angle of list, possible biofouling. OMG stands for a big appendage on the vehicle, and wing loss. And the first thing we can notice straight away, if we're looking at the yellow line, which is the autoencoder, is that we have a low anomaly score for healthy gliders, which is what we expect because we train on healthy gliders. And so for the autoencoder, it goes between 0.1 and 0.2 as normal. What we can notice straight away is the wing loss is detected as a sudden fault. So in this case, there was a big collision. And this is detected not only by the autoencoder, but it's also detected by the rule-based system in green and by the model-based system in purple. Then the second thing we can detect is biofouling. Now, unfortunately, I can't see whether you, no, it doesn't look like it's being shown. Yeah, so biofouling, we can actually detect a slow growth as well. And so in this case, what's happening here is that we can detect the slope, which is slowly increasing. And so we can detect that something happening in terms of additional marine growth on these long deployments. And this is very important for pilots to determine when the vehicle can be recovered, because once it reaches too high a weight, it will actually be lost. And the model-based system is able to pick this up as well. Another nice feature is the fact that the vehicle is able to generalize to different technologies. So here we see that the range for the OMG, so basically for the glider wave big appendage, is actually in the range without detecting anomalies. And this is fundamental because what's happened here is we've used the data for one vehicle variant, and actually we've seen that we can transfer that knowledge to other vehicle variants without problems. Now, the only problem with the autoencoder is that it doesn't detect the angle of list. And this is because of the signals that are used by it. So the BiGAN is actually different. In this case, it's actually able to detect it, also because it's looking at time series data as compared to steady state data. And so what we can see is that you can tell the difference from the healthy baseline. And I guess the final lesson that is pretty fundamental from the slide before we conclude is that the model-based system and the rule-based systems are only in 3 plots because they're very problem specific. It took me a long time to design them for very specific tasks. And so actually it takes a lot of time to design them for every single failure. Whereas the model-based solution, the data-driven solution was able to detect and adapt to many, many faults by itself. Basically, it didn't matter what the faults were, it was able to detect them. And this happened in an unsupervised learning way. So it was completely unsupervised learning. Nothing came in from the user. So what are the lessons learned from this better case study for machine learning? Well, machine learning is definitely more general. So this means that it's not only more applicable to different problems and easier to change to different problems, but it's also technology agnostic. So if you train it with a specific data set, you can transfer that knowledge to a different device with slightly different parameters, but it's still able to adapt to that pretty well. And this is quite important. Then it's got better scalability. It's very easy to increase the number of signals. It's very easy to increase the number of vehicles without making major modifications to the system. It's got a really high training cost. So actually training needs to happen on a cloud offline, but then once trained, you can deploy it at a low cost, and it basically takes the same computational time as a model-based or a rule-based solution. However, you got worse sample efficiency. We're talking about millions of points as compared to maybe the few data points that would be sufficient for a dynamic model. So this, again, is something to keep in mind when you're looking at machine learning for ship design. So in conclusion, I think that machine learning does have the potential to revolutionize the marine sector. There are many applications. And what is really nice about it, and we looked at only 2 case studies, but it's basically the generality and the scalability. So you can generalize it to different technologies, but also to different applications, and you can scale it to large scale pretty easily, as long as you do the training offline, obviously. And obviously the but is you need to be addressing the right problem. So you need to have framed the problem the right way, because otherwise machine learning is likely to return to you just rubbish. And you need to have very large quantities of data, which might be a problem for naval architects. Could be good in maneuvering, but for instance, in ship design, you need to create a lot of fictitious designs. So these are the references. Thank you for your attention. I hope this presentation has been of interest, even though I know it's not purely, it's not properly like naval architecture, but I hope that you probably have different applications to which you thought of applying machine learning to, or you've already applied it, and maybe different case studies and experiences.
I've got a question up straight away, and it's not surprisingly from a UCL colleague or professor, David Andrews. So, David, I'll just unmute you if you want to ask your question to Enrico.
Can you hear me?
Yeah, I can hear you.
Yeah.
Okay.
David.
Thank you for that, Enrico. I knew very little about machine learning, and you've given me a lot of information there. So I'm obviously interested in what it might mean for future ship design. So I wondered if you perhaps could say a little bit more about what you said about, because we can have very simple numerical synthesis models, which you know I'm not that happy with, but a lot of people use them. A lot of people have spreadsheets, and you can generate thousands of nominal designs. I'm very dubious about that, because if you don't get into enough sense of the architecture, you can have what numerically seems to be a balanced design, but of course it isn't really. But I wondered if you could just say, am I being a bit naive there? What's your feeling about using machine learning for design? I've got a sort of follow up to it if you don't quite understand what I'm
No. I think I understand it. But yeah, feel free to ask the follow up as well. So basically, like, this is my personal opinion. It's not obviously the UCL opinion or anything. My opinion of this is that basically there is definitely a potential. However, in reality, we know that actual designs are very limited. So what we looked at with a colleague at UCL, it was Andrea that looked into this, is that maybe for some small data sets, and he looked at a lot of ship design, looked into 300 actual ships from the arena, basically significant ships at the end of the year. And in that case, the data set was still like so limited that in reality, that's really the boundary between machine learning and statistics. Statistics may be more accurate because we're looking at actual small data set. However, what also is possible is, you can generate data, as you say, fictitiously, but then I think there needs to be a proper quality control in that. So you need to determine that basically those designs you generate are actually feasible, like they need to be feasible. And then if you're able to generate about more than 1,000 to 10,000 designs, then yes, there is a scope for machine learning to actually help out with designing a sort of a simpler tool that can be used in concept design, just to help designers, especially novice designers, from the very start to spot if they're making massive mistakes or not. Yeah. But basically this requires a lot of high-level experience, high-level designers to generate basically tools that are able to generate a lot of options, and then machine learning can be used to compress this information into just the meaningful information. Yeah. And this is something similar to what we've seen in the presentation from last year, and I might be wrong, but this was from the Ineos team, sailing team for the America's Cup by the UK, and they showed how they generated a lot of data in CFD, because obviously we're not looking at full ship design, we're looking at a America's Cup design where the the layout perspectives are more limited. And in that case, they were doing a lot of optimization on the flow. They generated a lot of data. They couldn't generate millions of data points because it's too expensive. So they use machine learning to try and fill the gaps between the samples they took. So machine learning is good to bridge the gaps between data points. What it's not really good of is going beyond the ranges of the selected data.
So we still need the human to do the creative bit.
Unfortunately.
I hope. Unfortunately not. No, absolutely. Otherwise, we're all out of a job, and we just we'll have a black box doing future ship design. No, I'm very much of the view that we use the machines to do the difficult bit, but we do the creative bit, and that's how we need to develop it. And that's a challenge for your generation. Let's see how we do that. No, that was my follow-up was really, I remember, because I'm very old, when expert systems first came along, and there were supposed to be two sorts of expert systems: those that look backwards based on existing, and those that look forward. And of course, we were all interested in the look forward, but I never ever got anybody to explain to me how the look forward was going to work. And I just wonder if the machine learning will also end up just being, dare one say, boring. It'll always go for the average. I mean, many years ago, before we had all the computery, we still had things like design lanes. And I remember David Brown, who taught me, a very wise man, he said the problem with design lanes, and it's a bit like your machine learning and your data sets, the problem with design lanes is that what you get is the average ship. Well, you know, who wants to design the average ship? You want to design the better ship. How do you if you just stick with the design lane, you're in the middle of the design lane, but actually the really good ships were, for whatever application you talk about, we're at the top end of the design lane. Do you see what I mean?
No, I see what you mean. So there is a positive and a negative. Machine learning, as compared to statistics, is able to deal with what you would call outliers. So basically those really good designs. It's able to capture them.
Right.
However, having said this, I would never trust machine learning to go beyond what is the maximum range in the data set. I would never trust a design that would go, say, machine learning is recommending to me to go that point, that high. I would never trust it, basically. I think that it will need to be still within the range. But machine learning is a bit better than classical statistics to deal with these like extreme points, which is, I agree with you, it's like the exciting, we want to push the boundaries forward. So that's why there might be a problem. Now, having said this is machine learning. There are different artificial intelligence methods, such as genetic algorithms that actually tend to generate new data sets. And so in that case, they can look at a lot of options. And if you include fully, fluid dynamic models, layout models, structural models, maybe they can actually investigate new areas autonomously. And then they can tell you, look, this is a point that might be interesting to look at. And as a designer, then you can try and find it and then check if what the algorithm is doing in that case is good or not.
Great.
I don't know if this makes sense.
No, that's very helpful. Thank you.
Okay, thank you, David. We have a couple of questions, I think, from Blanca. So if you want to go ahead with just unmute you.
Yeah, so can you hear me?
Okay, yeah, that's good.
Yeah.
Go ahead.
Yeah, sorry, I didn't text them because they're a bit long, maybe. So I thought that I prefer just to ask you directly. Enrico, your presentation was great, very informative. I really enjoyed it. I have a couple of questions, maybe more, I don't know, let's see. So my first question is about gliders. I never heard about gliders before. It's the first time ever I heard about these devices, these vehicles. So you mentioned that the hydrodynamic coefficients vary significantly with biofouling, etc. So by how much did they vary, these coefficients? Do you calculate percentages?
Yeah, well, they vary by 2 or 3 times as much. And the reason for that is because, not this one, but the other one, is it looks like it's got an ogival shape. And it's going to have laminar flow over 70% of the body, and then it goes into transition or just at the stern. Yeah. And so the problem is if you change that laminar flow into transitional early on, there is a massive increase in drag. And so that's why it actually ends up having 3 times as much drag as originally. Now, we looked at some extreme biofouling in the Canary Islands. That was really extreme, to be honest. But even like what looked to be lighter biofouling still had a very big impact. Now, this is not the case on ships. I think on ships, we quantified it to be.
Okay, so but what's the length of these devices, these gliders?
So this one is 2 meters, but the other one, the one that is really affected, is 1.8 meters.
Okay, interesting. Yeah, so in terms of hydrodynamics, that was my main question. Then I have questions about GANs. I work quite a lot with GANs, but I use them for different purpose, for different reasons. I mix them a lot with CFD, fluid mechanics, etc., etc. So you're using a big GAN. So where is your architecture? So where do you have the reference of where you base your architecture from, or you build your big GAN directly yourself?
No, thanks. Thanks for the question, Blanca. So actually, the Peng in the chart as well here is a researcher at UCL. Is the one that actually developed it. And so basically, we took the BioGAN from a publication. So the BioGAN, the only difference is you add the encoder, because in this case, we're trying to extract the fundamental features. So we're trying to extract the fundamental information from it. So we had to add the encoder. And then what actually Peng added was adding some hints on the data to make the learning faster as well. So we actually, we knew, like, we added hints in the training to make it better at deployment. So, I mean, to be honest, we can definitely send you the publication. It's
it would be interesting. Yeah, I quite
it's
like this topic.
It's this one.
Yeah. Okay. Okay. So, but for how many epochs? So, how long did it take this training, this actual training, so people here can understand how tough it is to train these networks?
Are you talking in terms of hours or in terms of?
Yeah, in terms of computational power, I guess you use the SPC cluster that UCL has with GPU units, etc. So
it took less than a day. It took like a few hours.
Yeah,
we did run it on the cluster. I forgot the data. Maybe Peng, if you know the data, you can provide it in the chat. But it's less than a day. It's like a few hours for training, and deployment is really quick.
Yeah,
so no,
but you use. Yeah, but I guess you use the GPU unit in a cluster, right? From the cluster.
The GPU is about, I don't know, probably 40 times faster than a CPU, I would say, maybe 10, depends on the application. But yes, we use the only GPU.
Yeah, depends on the GPU as well, because the one we have is quite powerful, I would say.
Yeah, so it takes about a couple of hours on the GPU. Yeah, that's what it does. So I would imagine if you were running on a CPU for this many million points, I think it was about 8. Can be wrong. Probably was a bit less because we use only 4. But yeah, I would imagine something like 24 to 32 hours as a sort of a range CPU.
Yeah, it takes quite a lot. Well, in my case, I'm training, for example, conditional generative adversarial networks, and it takes like days using my CPU little laptop. Well, I use the GPU, but it takes quite a lot of time.
Yeah, basically like Peng and myself also use the GPU on the desktop, and that is also much faster. You can actually do it in less than a day with that one as well.
Yeah. Okay. No, interesting. And the third question I have, it's about so these gliders. So how do they avoid collision? So collisions. So do they incorporate some sort of sensors like cameras or things like that? So have you worked with this?
No, unfortunately, they don't avoid collision right now, because the problem is these devices are designed to be, they're a sensor for oceanographers, and so they're designed to be at sea for 12 months. Sometimes the Oceanography Center typically uses them between 3 and 6 months, but basically they have to be there for a long time. And so the computing power is very limited. They actually have a sample rate of 5 seconds on board, and the decimated data is every 30 seconds. So we're talking about really, really slow. And there is no collision avoidance whatsoever. So the pilot has to select the next waypoint. And so the reason why it lost the wing is because it probably hit a whale or a ship, and it just basically lost the wing that way. That's why it was a sudden event. There is no collision avoidance whatsoever. So that's why the path planning is also being one of the things we'll probably look at, because You want to avoid shipping lanes, and at the moment, this is something still done by the pilots. So these are very, very flexible devices, really, really cheap. They cost $150,000 to $200,000. They're really good at sampling data, but they're really super efficient. And to be that, they basically, they drop a lot of things. Like an AUV, a commercial AUV typically lasts 4 to 5 days maximum in operation, maybe even 2 weeks if it's like a hybrid. But these guys last month, and that's because they're really, really simple. They basically have as little computing power as possible.
Okay, interesting. Thank you.
Yeah, no, thanks.
Okay, thanks, Blanca. We have the next question from Laura Marimon. So just let me unmute.
Hello.
Laura. Okay, Laura.
Yes, Enrico, thank you very much for your interesting presentation. I have a question on shifting from gliders and underwater vehicles to actual ships. We see now a shift into kind of renewable or fossil free, and so wind carriers, for example. So normally you have a ship, but until now they have some systems fitted into it, and they're well integrated in all the systems of the ship, and officers are able to use them very well. But when you start adding sails, for example, or new propulsion systems, how do you see machine learning working in that area? Whereas you just said it's quite difficult to extrapolate from points that are unknown. So do you see that as an area that will develop in the future, or is that too early to get machine learning from, I don't know, when they need to reef the sails or things like that?
Hi, Laura, thanks. So no, we definitely want to go that way. We want to go the full large-scale marine autonomous ships direction. Now, the wind assisted propulsion is more tricky, so we come to that. Now, for machine learning, we do need the data. If we don't have the data, because there are not many marine autonomous systems right now, the idea we're having is to go from fictitious data generated from simulations, learn from that, and then use something called transfer learning. So we adapt the domain and the data distribution to the full-scale ship, and to do that, we pass through experiments. Now we start to get in touch with a lot of large operators of marine autonomous systems, and we're talking about small marine autonomous systems because they're still lower than 24 meters. There's a few operators that are going bigger, but basically we started to look at, we work with them. And the biggest problem, as you mentioned, is, I mean, it's a completely different scale. The system is general, so we're able to apply the fundamentals to that problem, but it means that we will need to revisit everything we've done to go into more detail. The failure mode and effect analysis is much more complex. The machinery is going to be, I mean, way more complex than this vehicle. And actually that's probably where most of the faults are happening. So a lot of these marine autonomous systems, from conversations we've had with these companies, are actually designed to be super reliable. They have a lot of redundancy to try and determine how to survive. And in that case, I think like the fundamental question that would be probably interesting to address is having a full tolerant mission planning. So after a fault happens, how can you keep your capability, or even can you continue your mission with reduced capability? That's basically where we're going. And with wind assisted propulsion, that's really tricky, because not only you have the machinery, which is already complex, and also the batteries and like a hybrid system, integrated electrical propulsion, which is going to be complex. But as you say, you have all the foils, you have the wings as well. So it becomes a very difficult problem. So I think machine learning definitely has a way to solve it, because having a lot of model-based solutions or rule-based solution is going to be really heavy on the designer. However, I think that for such complex systems, unfortunately, you need to start from rule-based and model-based solutions, and those will be operative from day one. But in the meantime, simulations can be used to generate fictitious data to try and develop the machine learning equivalent. You can test it in the experiments, and then once you have, say, about, I don't know, 6 months to 12 months of data, then at that point you can build some confidence in the validation of your machine learning. And at that point, if it works better, you can like sort of substitute it. And actually, the main reason is because the machine learning system is also able to detect if there are changes in the system behavior with time. which are very tricky to model otherwise. So I'm not sure if I'm answering. I think unfortunately, rule-based and model-based will need to be done for the prototypes, but the hope is that long-term machine learning will be able to.
So it's basically a vision to integrate machine learning in these new kind of digital twins that are being developed kind of everywhere as simulators.
Exactly.
Yeah. Thank you very much.
Yeah,
Good presentation.
Yeah, thanks.
Thank you, Laura. We have one question in the chat box, Enrico.
Yep.
It says, as the complexity, and this is from J. Partridge.
Yep.
He says, as the complexity of the system increases, the number of possible failures increases. Do you envisage that a single algorithm could be trained to a wide range of possible failures, or would specific algorithms for certain aspects of a vessel be more appropriate?
I think there will need to be, for marine autonomous systems, probably a sort of like a pyramid as well of systems. So having additional redundancy as it's being done on planes right now. And so I think there is the possibility to have a single system. And something else I haven't mentioned is the underwater gliders are really basically limited on computing power. So actually the full diagnostics, the data-driven solution is done offshore, it's done on a cluster. With ships, you can actually have enough computing power on the ship to actually have a solution both ashore and a solution on the ship to increase redundancy and also survive lack of communications, which can happen. Then the second thing is, answering to Julius, yes, you will need to have, I think that having a more specific system, especially for the machinery and the energy management to the batteries for high integrated electrical propulsion will be fundamental, because that's going to be much easier to train and develop. But having a sort of a global solution, I think would be really interesting to have as well. Maybe using fewer sensors, so just the fundamental sensors, to try and limit the number of sensors we put on ships. Having something like a sort of a system that is global, I think would be really, really interesting. And that's basically what interests me. But I recognize that we have to be pragmatic. And I think that having multiple specific subsets dedicated to the different areas of the ship will probably be the way forward. So to have the added redundancy and provide, basically meet something like almost like BP2 regulations, like going into mass.